Hello students, today we're going to do a practical on surface area to volume ratios and why this is important for cells. So you've learnt so far that the cell membrane is the barrier which separates the internal parts of the cell from the external environment. Now it's through that membrane that the cell receives all its raw materials for all its metabolic processes inside. So we just look at oxygen, for example. Oxygen has to diffuse from outside the cell into the cell. It does that through the cell membrane, which is the surface area of the cell. And now that oxygen's got to diffuse all the way to where it's needed within the cell volume. So we have an interesting problem here where the surface area actually has to feed the volume. And what we're going to do is a little experiment that looks at how this is changed by cell size. So we start with small cells. We're looking at a large surface area through which oxygen can diffuse through to diffuse throughout the volume of it. And then we're going to compare that with large cells where the surface area to volume ratio, because it increases as the square, quickly lags behind the volume, which increases by the cube. And we're going to do that using some agar gel, which is infused with phenolphthalein, which is a pinkish colour when it's alkaline, so this has got a slight alkaline consistency to it. And we're going to look at vinegar passing into these agar blocks, cut to cubes of different sizes, and just seeing how the vinegar diffuses into cubes of different sizes and how we relate this to surface area to volume ratios.
We're going to start by drawing our cubes that we're about to cut up into our agar gel. So we're going to start with a 1 by 1 by 1 cube. We're now drawing a 2 by 2 by 2 cube. And next we're going to finally do a 3 by 3 by 3 cube. Now these are representing the cubes that we're going to cut out from the gel, and we're going to now work out the surface area and the volume of these cells, or these cubes, so that we can work out the surface area to volume ratio and predict what's going to happen. So to start with that, we're going to need to calculate our surface area. Now in order to calculate surface area, it's length times width times by the number of sides. Now for a cube, that's going to be 6 sides. So we'll work out the surface area for each of these cubes now. So starting with a 1 by 1, so surface area of one side is 1 by 1, which is 1 centimetre squared. And we're going to times that by 6 because there's 6 sides on the cube, which gives us a total surface area of this cube of 6 centimetres squared. Now if we're looking at the 2 centimetre cube, it's 2 by 2. Again, times by the number of sides, which is 6, so 2 by 2 is 4. 4 times by 6 is going to be 24 centimetres squared. Finally, we'll look at the surface area for our 3 by 3 cube. Now the 3 by 3 cube is 3 by 3. Times by 6 again for the number of sides, so 9 times by 6, and we are going to end up with 54 centimetres squared for the surface area for this larger cube. Now to work out the surface area to volume ratio, we also need to work out the volume. So let's have a look at volume here. So to work out volume, it's length times by width times by height. So again, we'll work out this for each of the cubes. So the first cube, 1 by 1 by 1, our volume is 1 centimetre cubed. Now looking at the 2 centimetre cubed, it's 2 by 2 by 2, which is going to end up to be 8 centimetres cubed. Finally, we're looking at our 3 centimetre cube, which is 3 by 3 by 3, which is going to end up being 27 centimetres cubed. We now need to work out the surface area to volume ratio, so that simply involves us dividing the surface area by volume, which we'll just write down here. So let's work out the surface area to volume ratio for each of these cubes. So 6 divided by 1, that's going to give us a surface area to volume ratio of 6 for this 1 by 1 cube. Next, for this one over here, 2 centimetre cube, 24 divided by 8, that's going to give us a surface area to volume ratio of 3. So 24 divided by 8 is 3. Lastly, we're going to be looking at our 3 by 3 cube, so 54 divided by 27. That's going to give us an answer of 2, so a surface area volume ratio of 2. Based on this, we can say that because the surface area to volume ratio is higher for the 1 by 1 cube, based on the calculations we just did on the iPad, we're now going to cut out some cubes that are 3 by 3 by 3 centimeters, 2 by 2 by 2 centimeters, and 1 by 1 by 1 centimeters. So we're going to start off, as you can see here with the ruler, we have got our agar gel that is 3 centimeters thick. So we're then going to cut that so it's 3 centimeters wide. And we're also going to cut that so that it's 3 centimeters long. And we have our agar cube of 3 by 3 by 3. We'll now do the same thing for agar gel that's 2 centimeters thick. So we will cut first off 2 centimeters long. And we have our agar gel cube of 2 by 2 by 2. Finally, we'll do this with some gel that's 1 centimeter thick. This is a different color because it's from a different batch of agar. It's still the same gel. We want to have 1 centimeter thick. And we now have our 1 by 1 by 1 cube.
Cubes that we have now removed from the vinegar, we can see that on the borders and edges of each gel, so we've just taken a cross section of them, there is some discoloration and a change in texture and consistency of the gel in that border. So in comparing the gel sizes, we can see that our smaller cell cube is far more efficient. We have that change in consistency and color being far greater seen in comparison to our larger agar gel cell.